Hello everyone, let's come to the third section. Cholesky factorization for the symmetric and positive definite matrix. Okay, so here I will introduce you a special factorization named Cholesky factorization, and also for special matrix. So here, the symmetric and positive definite matrix. Okay, we have learned LU factorization. So this is a special case for special matrix. Okay, firstly, what is a symmetric matrix? We know a square matrix A is called symmetric if A equal to A transpose, right? Here, AT, the capital letter T means the transpose of A. You should understand, right? Okay, and what is a positive definite? It means if for any or for every n-dimensional vector, non-zero vector x, you use x transpose multiply A multiply x. Okay, we know x is a column vector, right? A is a square matrix, so x transpose is a row vector. A row vector multiply matrix, square matrix, and multiply column vector. The result is a number, right? The result is a number. Okay, if this number is always positive, no, you should know here, always positive number for every non-zero n-dimensional vector x, then we call the matrix A is positive definite. That's okay for you? Positive definite. Okay, so now in this section, we consider this special case when A is symmetric and positive definite. Then let's see what's the special LU factorization. It's okay? And I hope you will remember there are some good properties for positive definite matrix. For example, the positive definite matrix is equivalent that all the ordered principal minus of A are positive. Okay, so here the ordered principal minus, for example, decay, it is a determinant of the submatrix minus, right? A11 to A1k and AK1 to AKK. The K times K order submatrix for A, right? Okay, because we suppose A is a positive definite, so it is equivalent that all the ordered principal minus decay, they are positive, greater than, bigger than 0, when k from 1 to n, all the ordered principal minus. That's okay for you? Okay, so by the theorem, the existence and the uniqueness of LU factorization. Do you remember the theorem? The theorem said, okay, the sufficient condition for LU factorization is all the ordered principal minus are not 0, right? Now here, we suppose it is a positive definite, so all the ordered minus are positive, not 0, greater than 0. Okay, so that means a positive definite matrix A always has unique LU factorization. Unique factorization. That's okay for you? Okay, so that means for this special case, positive definite, we always can obtain LU factorization. So now let's consider the result. Assume that A is symmetric and a positive definite matrix. Then we know it has unique LU factorization, right? We denote it by L and U. Okay, so U we know it is an upper triangular matrix, right? Like this, right? Upper triangular matrix. Okay, now if we denote U11, U22 to UN, they are the diagonal elements of matrix U. Now we can also factor U into the product between the diagonal matrix. Multiply this new upper triangular matrix with ones on the diagonal. It's okay for you? For example, let's show you 2, 3, 0, 4. For example, this is a upper triangular matrix, right? Okay, we can factor it by, take diagonal elements to obtain a diagonal matrix 2, 0, 0, 4. It's okay? Then multiply a new matrix, upper triangular matrix. Okay, so that means you should know here, we use this row, first row multiply first column, right? Okay, so because it is 2, so 2 multiply 1 multiply 0, here also 0, because we will obtain also upper triangular matrix, right? Okay, and so for the 3, this element, it is first row multiply second column, right? So actually it is 3 over 2. And the last element is 1. It's okay for you? So you use 2, 0 multiply 1, 0, you will obtain 2. You use 2, 0, first row multiply second column, you will obtain 3. It's okay? And you use second row multiply first column, you will obtain 0, right? And you use second row multiply second column, you will obtain 0 multiply 3 over 2 multiply 4 plus 4 multiply 1. It is just 4, right? It is okay? So that means we can factor the general upper triangular matrix by a diagonal matrix. Okay, multiply a new upper triangular matrix with ones on the diagonal. So you see, this diagonal are ones. That's okay for you? Okay, so continue. Okay, we denote the diagonal matrix by D. It's okay? By D. And the new upper triangular matrix with ones on the diagonal denoted by U tilde. It's okay? Then, okay, we know A is L multiply U, and now U is D multiply U tilde. Okay, and also we have another condition. A is symmetric. That means A is equal to A transpose, right? Okay, so you should know transpose. We know for the operation, the product, okay, the transpose of product AB equal to B transpose multiply A transpose. It's okay? Okay, so that means here, if we consider A transpose, then that means LDU tilde transpose, right? It's okay for you? So continue. You should write last matrix U tilde by transpose multiply D transpose multiply L transpose. It's okay for you? By the rule, okay, you will obtain U tilde transpose multiply D transpose multiply L transpose. It's okay? And the left side is A, so L D U tilde. Right side is A transpose here. So first is U tilde transpose. Because D here is a diagonal matrix. So D diagonal matrix, the transpose is not changing, right? DT is just the D. It's okay? And here, L transpose T. Okay? So here, now let's continue. We know U tilde is this upper triangular matrix with ones on the diagonal. If you consider its transpose, what it mean? That means you put all the elements on the upper triangular part into the lower triangular part. It's okay for you? So that means U tilde transpose is also a lower triangular matrix with ones on the diagonal. It's okay for you? And similarly, L is a lower triangular matrix, so its transpose is an upper triangular matrix. And don't forget, L is with ones on the diagonal, right? And also D is a diagonal matrix. Now you see what it means. If we consider U tilde transpose, we know we also obtain another LU factorization for the same matrix A. It's okay for you? Now we obtain two factorization, but we already know A should has only one LU factorization. So that means L should be equal to U tilde transpose. It's okay? So we obtain L should be equal to U tilde transpose, because they are lower triangular matrix with ones on the diagonal, so they should be same. Also, D U tilde should be equal to D L transpose. It's okay? So we know L equal to U tilde transpose. That means U tilde equal to L transpose, right? Okay, so by the uniqueness of L and U, LU factorization, okay, we know here L should be equal to U tilde transpose. Are you clear? So that means, in fact, okay, here I need to clean the, okay? In fact, A here from the beginning, A equal to, by the, okay, LU factorization equal to L D U tilde. But now we know U tilde is just L transpose. It's okay? So now here we revise U tilde by L transpose. Okay, you see, we obtain the special structure of factorization for A, because A now it is a symmetric and a positive definite matrix. It's okay for you? Okay, continue. Let's consider the diagonal matrix D. Diagonal matrix D. So you should use the property definite matrix, the property of a positive definite. Okay, we just said in the last slide, we know the positive definite means all the ordered principal minus they are positive. They are positive, right? And also we know by the eigenvalue, because we already know U is the upper triangular matrix, right? So we know the determinant, the minus. Here you should know D1 just we know because A equal to L multiply D multiply U, and we know, I write here, I clean. Okay, now from original equation, now here we know determinant of A equal to determinant of L multiply determinant of D and multiply determinant of U tilde. It's okay? By the property rule of determinant. L is a lower triangular matrix with ones on the diagonal. Okay, so the determinant of L is just 1. Okay? And what is the determinant of U? Of D? Here is D. Okay? We know D is a diagonal matrix, so its determinant is just the product of all the diagonal elements, right? So it is U11 multiply U22 multiply to UNN. It's okay for you? And multiply the determinant of U tilde. U tilde is also a upper triangular matrix with ones on the diagonal. So its determinant is just 1. It's okay? Okay, now you should know here. The determinant of A is just U11 multiply U22 multiply to UN, the product of all the diagonal elements of U. Also, we know for the minus D1 just equal to U11. And we know D1 is positive, right? Because A is a positive definite matrix. So D1 is positive. That means U11 is positive. And D2, the minus equal to U11 multiply U22. It's okay for you? Okay, and also we know because A is a positive definite, so D2 is also positive. Because U11 is already positive, so we know U22 is also positive, right? By the first D1, we know U11 is positive. So continue, we know dk is a product of U11 multiply U22 multiply UKK. And it is positive. Okay, we know all the elements should be positive, right? So UKK also positive. Okay, it means the diagonal matrix D, all its diagonal elements are positive. So we can use this symbol, denote the diagonal matrix with square root U11, square root U22, and square root UNN as the diagonal matrix. It's okay for you? Just like we consider the square root of D. Okay, we use this symbol, notation. It's okay for you? Because we suppose A is a positive definite matrix. So all the elements, diagonal elements, should be positive. It's okay? So that means we can separate, that means D, the diagonal matrix equal to D1 over 2 multiply D1 over 2. It's okay for you? Now I clean here. From this equation, that means we can separate D into D1 over 2 multiply another D1 over 2 multiply L transpose. It's okay for you? Now we use another matrix denoted by L tilde to represent L multiply D1 over 2. That means we use combination here. It's okay for you? So the first part denoted by L tilde is L multiply D1 over 2. What is the second part? Can you tell me? Okay, it is just L tilde transpose. It's okay for you? It's okay? Okay, now from here, L tilde is L multiply D1 over 2. So L tilde transpose, by the rule, it should be D1 over 2 transpose multiply L transpose. And D1 over 2, it is also diagonal matrix. So its transpose is not changed, right? Just itself. So D1 over 2 multiply L transpose. Now you see, just the second part. It's okay? So it is just L tilde transpose. Okay, we know L is a lower triangular matrix. L is a lower triangular matrix with ones on the diagonal. And D1 over 2 is a diagonal matrix. So the product L tilde just a lower triangular matrix. It's okay for you? Because you multiply L from the right side by a diagonal matrix. It's just don't change the structure, lower triangular matrix. It's okay? Okay, now that means we can obtain a special LU factorization for the symmetric and positive definite matrix A by A equal to L tilde multiply L tilde transpose. It's okay for you? So this is a special factorization of symmetric and positive definite matrix. Are you clear? Now from the beginning, LU factorization by the uniqueness, then we obtain this result. Okay, this is the Cholesky factorization. That means a special case for symmetric and positive definite matrix A. Are you clear? Okay, so next we only need to consider, because you see A equal to L tilde multiply L tilde transpose. L tilde is a lower triangular matrix, so we only need to know what is the lower triangular matrix. If you know L tilde, you know L tilde transpose. Are you clear? So we don't need to use Gaussian elimination. We can obtain the L tilde directly by the product rule of the matrices. Can you understand now in this section, we just consider the special case. For the general case, we need to use Gaussian elimination to obtain L matrix and U matrix, right? But now, because we just consider the special case, symmetric and positive matrix, by the theoretical analysis, we know A equal to L tilde multiply L tilde transpose. But now, we can obtain L tilde directly, not need to use Gaussian elimination. It's okay for you? Okay, in conclusion, we obtain a theorem, Cholesky factorization. Now we know for any symmetric and positive definite n by n square matrix A, there exists a lower triangular matrix L. Now, we just use letter L to represent the lower triangular matrix. Now you should know, we don't say with ones on the diagonal. It's okay for you? So you should know the difference. Now, we just said L is a lower triangular matrix, general lower triangular matrix. That means its diagonal elements are not ones, okay? Are not always ones, okay? Such that A is just equal to L multiply L transpose. This is called the Cholesky factorization of A. Further, if all the diagonals of L are positive, then the matrix L is unique. Now you see, we just said the diagonal elements of L are positive, not always 1, okay? But we can suppose they are positive. Then, in this case, L is unique. Okay, so this is special LU factorization. We call it by Cholesky factorization. Now, we introduce the following also named Cholesky algorithm to obtain L, the lower triangular matrix, directly. Okay, we don't use Gaussian elimination. We want to obtain the Cholesky factorization directly. It's okay for you? You should understand the idea. Okay. Now, let's come to the algorithm. Actually, you just need to practice by some special example. That's okay. You can master the algorithm, the idea. Okay, the question is, we are given the matrix, square matrix, because it is symmetric and definite, positive definite matrix. We want to factor it into L, this matrix L, lower triangular matrix, multiply its transpose. Okay, so here, we denote the elements for L. First column L11, L21 to Ln1. Second column L22 to Ln2. Okay, last column just Ln. It's okay? Okay, this is L and multiply L transpose. Okay, transpose means, now you see, you transpose, you put the first column here to the first row, right? So L11, L21 to Ln1. Second column to second row, L22 to Ln2. Okay, last column to last row. Clear? This is transpose. Okay, so now our aim is to obtain all the elements L11, L21, Ln1, right? Okay, so actually now we can just use the product rule. Let's check. The first element A11. How to obtain A11? By the product rule. You should use the first row multiply this first column. It's okay? Because all the elements are zeros. So only one element. L11 multiply L11. So square. It's okay? Okay, so now you know A11 equal to L11 square. So directly we know L11 is equal to square root of A11. Okay, now we know we can choose the positive square root, right? It's okay? So that is why we can suppose L is positive. The diagonal elements. Clear? Okay, so now we obtain L11 directly, right? Next, let's consider to obtain L21. Okay, now let's check A21. A21 is the second row first column. So we need to use the second row of L multiply the first column of L transpose. Clear? Okay, so it should be L21 multiply L11 plus L22 multiply 0, right? And plus other zeros. So directly A21 is just L21 multiply L11, right? And we already obtained L11 here. So now we can use it to obtain L21 is A21 divided by L11. Clear? Now we obtain L21. Similarly, okay, for the general case, for example, I write here AK1. In the case row, right? Case row next element is AK2 to, okay, here AKN, right? Now we just check AK1. AK1 is case row first column. So you should use case row LK1, LK2 to LKK, right? Because it's a lower triangular. So other elements are 0, right? Okay, you use case row multiply the first column. Because for first column, all the elements below the diagonal are zeros. So actually, just obtain AK1 equal to LK1 multiply L11, right? Okay, we can obtain LK1 equal to AK1 divided by L11. It's okay for you, right? Okay, so we can obtain the last element AN1 equal to LN1 multiply L11. So we can obtain LN1 equal to AN1 divided by L11. It's okay for you? So that means we firstly obtain the elements of the first row or first column for L. It's okay? Okay, so next we should consider to obtain L22. Now we focus on A22, right? It's okay for you? So what is A22? A22 is the second row, second column. So you should use the second row multiply second column here. So for this second column, only two elements, L21 and L22. So it is just the L21 square multiply L22 square. Because we already know L21 here. So that means L22 equal to the square root of A22 minus L21 square. It's okay for you? Okay. Now, next, we can consider, for example, if I write here, okay, A32, then here we have L31, L32, and L33. It's okay? The third row. Okay, so we know A32 should be L31 multiply second column. You should know here, just L21. It's okay? Plus L32 multiply L22. It's okay for you? Okay. L33 multiply this is 0, right? Okay, so just the two terms. And we already know L31, right? L31 first column we already know. L21 we already know. L22 already know. Okay, so we can obtain L32 by A32 minus L31 multiply A21 divided by L22. It's okay for you? So you see, we can obtain L32. Okay, so clear? Clear? So here, continue in the slide. We just use the product rule. Then we can obtain the general formula. Okay, let's check. Firstly, we need to use the diagonal elements AJJ, right? Okay, for AJJ, here, come back. Or for here, I use AJJ here. For example, I write here. Okay, I hope you also can practice, okay, by yourself. Okay, so AJJ is a JS row, JS code. Okay, so I change here. AJ1, LJ2 to LJJ, right? LJJ. So this is a JS row. And for JS column, also here I write here. For example, SJ1, LJ2 to also LJJ. Clear? Okay, so AJJ equal to LJ1 square plus LJ2 square plus 2 LJJ square. Clear? So it is the summation of squares, right? Okay, so here, if we write in the general formula, so AJJ equal to, okay, LJK, check here, LJ1, LJ2, LJ, so it is sigma K from 1 to J, right? LJK square. It's okay for you? But we put LJJ square and the single term, so the summation is from K equal to 1 to J minus 1 here. LJK square plus LJJ square. It's okay? Actually, that's same, right? And J from 1 to N. So the diagonal elements, right? And for other elements, Aij, and I from J plus 1 to N. So I is bigger than J, right? So let's check Aij. Aij I just write here directly. So that means ith row. So we have, okay, if you need to check ith row, okay, LJ1, LJ2. Now we use ith row. So Li1, Li2 to Lij, right? Okay, so ith row, Li1, Li2 to Lij, and to Lii, because I is bigger than J. Okay, this is case row to 0. Other are zeros, right? It's okay for you? Clear? I just write the ith row. The ith row. And multiply the JS column. You should know here is the JS column. Okay, JS column, so you should know it is should be L, also J1, LJ2 to LJJ. Are you clear? The JS column, because here this is L transpose, right? Transpose. So actually it's just the ith column, JS column of L, just put as column, right? It's okay for you? Okay, by product rule, you should use, so I write here, Aij equal to Li1 multiply Lj1. It's okay? First number multiply this number plus Li2 multiply Lj2. It's okay? Plus dots plus 2. Okay, now let's check. Here, we only have just non-zero number. Other numbers are 0. So actually, here 1, 2 to j. Because I is bigger than j, so actually we only consider plus to Lij multiply Ljj. Finish, right? Because other numbers here are zeros, so even here we don't have zero number, but product is 0, are zeros, right? Are you clear? So Aij by the general formula here, Li1 multiply Lj1, Li2 multiply Lj2, so here Lik multiply Ljk, and k from 1 to here, j minus 1. And the last term is Lij multiply Ljj. Clear? This is a general element, right? Aij. I bigger than j. I bigger than j. It's okay? So we stop here. Are you clear? Okay, now by the two formulas, the first one, we can obtain Ljj by square root of Ajj minus the summation k from 1 to j minus 1 Ljk square. It's okay for you to obtain the diagonal elements Ljj. And by the second equation formula, we can obtain Lij. Lij here just be Aij minus the summation k from 1 to j minus 1 Lik multiply Ljk, right? And divided by Ljj. It's okay? And I from j plus 1 plus j plus 2 and so on. It's okay for you? Actually, you should understand the here. You can check, okay? For example, here, now we come to here, A32, right? A32, you see, L31 multiply L21 plus L32 multiply L22. Okay, we already know L31, L21 already, so we can obtain L31, L32 by A32 minus L31 multiply L21 divided by L22. Clear? So that means we obtain the elements firstly, first column, right? From here I clean. From L11 to L21 and so on, and to obtain Ln1. Then come to the second column to obtain L22 here. Then we can obtain L32 and so on until to Ln2. Then move to the third column until to the last element Ln. Clear? So this is a Cholesky algorithm. That means we obtain L from a first column and then second column and third column and for last column. It's okay? So this is the order to compute the elements. Okay, one by one. Clear? Now you see, we don't use Gaussian elimination, right? We just use the product rule of the two matrices. Because A is a special case, so L and U, they are also special. A equal to L multiply L transpose. That is why we can use just the product rule to obtain Cholesky factorization. Clear? Okay, so this is the algorithm to obtain L. Now we know A equal to L multiply L transpose. And also we know if we want to compute the determinant of A, then it is equal to determinant of L multiply the determinant of L transpose. Actually, L is lower triangular matrix. L transpose is an upper its transpose is upper triangular matrix. For both cases, the determinant is just the product of the elements, right? They have the two matrices, they have same diagonal elements, so just LJJ square, right? So the product, you see? The product. Okay, so we can compute the determinant easily, right? To obtain by the Cholesky factorization. Also, if we want to solve the linear system AX equal to B, then we know A equal to L multiply L transpose multiply X equal to B, then we can suppose L transpose multiply X equal to Y, then here Ly equal to B, right? Okay, so just like Lux equal to B, remember? So here we can solve Ly equal to B firstly to obtain the vector Y, then put Y to the right side to solve L transpose X equal to Y. It's okay? So Ly is an lower triangular system. L transpose X is an upper triangular system. So first one we use forward substitution algorithm. Second one we use backward substitution. It's okay? So for the solving triangular system, we use the same forward substitution and backward substitution, right? But to obtain factorization, we use just the product rule. It's okay for you? Okay, so this is the LU, the special case, Cholesky factorization and Cholesky algorithm. Are you clear?